Hi, today's lesson is to do with combinations. Recall that our last lecture was on permutations. Permutations is a term used to refer to arrangements where order matters. So, the letters arranged as AB and BA are counted separately. In combinations, we are concerned with selections where the ordering doesn't matter. So, in this particular example, the letters AB and the letters BA would reduce to one selection of the letters A, B. That is the essential difference between combinations and permutations. Let's begin as usual with a simple example. How many pairs can be chosen from the letters A, B, C, D, E? A similar question in permutations would read, how many two-letter arrangements can be made from the letters A, B, C, D, E? The word arrangements there implies that the way the letters are arranged among themselves matters. In this question, we are concerned with how many pairs of letters can be chosen from the letters A, B, C, D, E. So let's list them. That's the simplest way. I can choose A and B, A and C, A and D, A and E. That takes care of all pairs which involve the letter A. And I can choose B and C, B and D, B and E. That covers all the B's that were left over. Then C and D, C and E. That's taken care of all the C's, and the last pair is D and E. So, having listed all the pairs in a very well ordered way, first picking all pairs that have the letter A, then picking all other pairs that have the letter B, and so on, I get my final answer, which is 4 plus 3 plus 2 plus 1 equal to 10 ways. Okay, let's stick with the same 5 letters. How many ways can I now pick 3 letters from A, B, C, D, E? Again, the word chosen implies that I'm not concerned with ordering the letters among themselves. Again, I'm going to list the ways. A, B, C, A, B, D, A, B, E. A, C, D, A, C, E, A, D, E. So now I've covered all triplets that have the letter A in them. Let's move on. B, C, D, B, C, E, B, D, E. Now the B is also taken care of. There's just one triplet left. C, D, E. So we again see that we have 10 ways of choosing 3 letters out of 5 distinct letters. Do you think it's a coincidence that the two answers were equal? That is, the number of ways of choosing 2 letters out of 5 letters and the number of ways of choosing 3 letters out of 5 letters. Or is there some link? Perhaps because 2 plus 3 equals 5. Think about it. We'll come back to this in some time. Okay, let's set up some notation. N choose R. This is the binomial coefficient. It's written as parenthesis NR or NCR, or sometimes CNR. It's read n choose r, the number of ways of choosing r objects from n distinct objects. In our previous examples, we had calculated 5 choose 2 to be 10 and 5 choose 3 to be 10. Of course, we had actually listed the ways to calculate these answers. We hadn't really figured out a formula yet. So let's go back to that example. List the number of ways of choosing 2 objects out of 5 and the number of ways of choosing 3 objects out of 5. So I choose A and B, and corresponding to that, I choose C, D, E. So this is the 2 objects and this is the 3 objects being chosen. Of course, from the set A, B, C, D, E. Then I choose A, C, and correspondingly I choose B, D, E. And I choose A, E, and I choose B, C, D. B, A, C. Oops, I forgot an A, D. That's okay. And I choose B, C, E. Then I choose B, C. So I choose A, D, E. I choose B, D. So I choose A, C, E. I choose B, E. So I choose A, C, D. I choose C, D. So I choose A, B, E. I choose C, E. Correspondingly choose A, B, D. And I choose D, E, which gives me A, B, C. So this seemingly random behavior on my part actually has something behind it. So I've split the set of 5 objects into 2 objects and 3 objects. So when I pick A, B, what I'm left with is C, D, E. So that's the 3 objects I've chosen. Actually, I haven't chosen them. They got left behind when I chose A and B. Similarly, when I chose A, D, what got left behind was B, C, E. Similarly, when I chose C, D, what got left behind was A, B, E. What have I really done? When I chose A, C, what got left behind was B, D, E. So what am I doing? I'm setting up a one-to-one correspondence between the set of 2 objects and the set of 3 objects. Every time I pick 2 objects, it's actually the same as picking 3 objects because those are the objects left behind. It's just a matter of language which was picked and which was left behind. Similarly, I could have picked 3 objects, say A, C, E, and I would have had B, D left behind, or A, B, C, and I would have had D, E left behind. So this one-to-one correspondence is beautiful. It shows me that the number of ways I can pick 2 objects out of 5 is exactly the same as the number of ways I can pick 3 objects out of 5. I've actually proved that 5 choose 2 is equal to 5 choose 3. I don't even need to know how much 5 choose 2 is and how much 5 choose 3 is. I've just proved that these 2 numbers are equal. So that's the heart of the proof. Show that the number of ways of choosing r objects out of n is equal to the number of ways of choosing n minus r objects out of n. That is, we want to prove the following equation. N choose r is equal to n choose n minus r. N choose r, of course, denotes the number of ways of choosing r objects out of n. And n choose n minus r denotes the number of ways of choosing n minus r objects out of n. The proof is simple. I list the n objects. A1, A2, A3, all the way to An. Here are my n distinct objects. N choose r wants me to pick all r subsets of these n objects. So I'll pick one such. Let's say I picked A1, A2 to AR. What's left behind? the other n minus r. ar plus 1 all the way to an. We're familiar with this argument now. Every time I pick a different subset of R objects, I'm actually also picking a different subset of n minus R objects. Those are the elements left behind. So you can see that there is a one-to-one correspondence between every R set and every n minus R set. Therefore, the number of R sets must be equal to the number of n minus R sets. We have proved that NCR is equal to NCn minus R. That is, n choose R is equal to n choose n minus R. Let's tidy these R's. Okay. This is a very fundamental way of thinking. I don't even know the formula for n choose R yet, but I've still proved a beautiful identity. Okay, before we go any further, I'm sure most students are cracking up that there is no formula introduced for n choose R. And I know most of you know the formula. What's going on in this lecture? Okay, so let us devise a formula for n choose R. How do we go about getting such a formula? So we have n objects, a1 to an, and we want to count the number of ways we can pick R such objects. Well, I don't know how to start, so I will go back to the permutation situation. I'm going to count the number of ways I can arrange R objects when I have n distinct objects. That we do know how to do. That answer is n for the first object, n minus 1 for the second object, n minus 2 for the third object, all the way for n minus r plus 1 choices for the rth object. And by the multiplication principle, I multiply all these r numbers out and I have the number of ways I can arrange r objects out of n. These are the arrangements. This was done in the last lesson. Now the problem is, these arrangements of course are too many, because say one of the arrangements is A1 to AR. However, these R elements will also occur in an arrangement A2 A1 dot dot AR or AR A3 dot 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 A2 and so on. All these arrangements are distinct. However, the question I'm looking for is the number of R selections. So all these arrangements should compress into one selection as far as I am concerned. So how many of them are there? How many such arrangements compress to one selection? That answer is simple. These are R distinct objects. In how many ways can I arrange? I can arrange them in R factorial ways. So, in this answer of permutations, there are R factorial arrangements that compress to one selection. There are R factorial other arrangements that compress to another selection, and so on. So I can divide up this huge number of arrangements into groups of R factorials, each of which converge to one single selection. Therefore, I now have the answer I'm looking for. The number of selections of R objects is the number of arrangements of R objects, which is this magnificent number, divided by the number of arrangements of each particular R object that I select, which can among themselves be arranged in R factorial ways. That's the formula you're familiar with. Let's go back and see how this formula works for our previous examples. So our first example was choosing two objects out of 5 distinct objects. So we had n equal to 5, r equal to 2. We wanted NCR, which is 5C2, which is 5 into 4 divided by 2 factorial, which turns out to be 10. Our second example was picking 3 objects out of 5. N equal to 5, R equal to 3. So we wanted NCR equal to 5, choose 3, which is 5 into 4 into 3 over 3 factorial, which is again 10. So our listing was correct. We do have 10 ways of picking 2 objects out of 5 and 10 ways of picking 3 objects out of 5. Of course, by the beautiful formula NCR equal to NCN minus R, I don't need to calculate both of them. I've already proved that these two numbers are equal. Now that I have a formula for finding out N choose R, I'm set. Okay, let's start using this formula. You have 9 different detective novels. Then how many ways can you select 6 novels to take on your holiday? Okay, just apply this formula. N is 9, you want to choose 6, so R is 6. And the answer is 9, choose 6, which expands to 9 into 8 into 7 into 6 into 5 into 4. 6 numbers upon 6 factorial. There's your answer. Feel free to calculate it. Okay, we're going to stay with this example and develop it as far as we can. You have 9 different detective novels. Then how many ways can you select all 9 novels to take on your holiday? All 9, N equal to 9, R equal to 9. Do we need a formula for this really? You want to pick all 9 novels, you have only 9 novels. How many different ways do you think you can get it? Well, one way, you just take them all. Let's see if the formula works. So I want 9, choose 9, which is 9 into 8 into 7, all the way down to 1 upon 9 factorial, which is 1. Wow, it works. In how many ways can you pick no detective novels? Okay, this is a tricky one. I don't want to pick any novels. Is there actually a way in which I can do it, or there are no ways I can do this? There is a way I can do it. I just don't take any novels. That's a way. I want no novels and I don't take them. So I actually have a way of not taking any novels. Therefore, the number 9, choose 0 should equal 1. Does it? I don't know. We have to define it as such. Our formula doesn't work here. So let's define it now. Let's define N choose 0 to equal 1. Is this a reasonable definition? I think it is. What this says is, in how many ways can I pick 0 objects when I have n objects? The answer is 1. I can pick 0 objects out of n by not picking any objects, and that is a valid way of doing so. So NC0 is 1. And how many ways can I pick 1 detective novel? So I want 9C1. Well, that's 9 upon 1 factorial, which is 9. And that's basically common sense. Who needs a formula to figure out in how many ways I can pick one thing out of 9 things? Well, obviously 9 ways. I just pick any one of them. So essentially, we've learned all the extreme cases. We've learned what NCN is, that's always 1. What NC0 is, that's always 1. And what NC1 is, that's always n. You don't need formulae to figure these out. You just need common sense. Let's move on to something slightly more interesting. You have 4 different maths books and 3 different history books. So 4 maths books and 3 history books. They're all different. In how many different ways can you choose 2 books? Well, does it really matter which 2 books I choose? No. So the fact that they're maths or history is really irrelevant to this question. What's important that they're all different books. And how many books do I have? I have 4 plus 3 equal to 7 books. And how many books do I want to choose? 2. So the situation is n equal to 7, r equal to 2. And the answer is 7 choose 2 equal to 7 into 6 over 2 factorial, 21 ways. So there are 21 pairs of books I can choose if I have 7 books. Sticking to this example, you have 4 different maths books and 3 different history books. 4m, 3h. In how many different ways can you choose 2 maths books and 2 history books? Okay, so I want 2 maths and 2 history. Well, the 2 maths books aren't coming from all the 7 books. They're just coming from the 4 maths books. So basically, a sub-question that I need to answer is on how many ways can I pick the 2 maths books when I have 4 different maths books? And I know that answer. That's 4 choose 2. Similarly, the 2 history books are only going to come from the 3 history books that I have. And in how many ways can I get 2 history books out of 3 different history books? Well, 3 choose 2. So now I have the number of ways I can pick the 2 maths books, and I have the number of ways I can pick the 2 history books. But I want both. There's this wonderful and looming large. So what do? I bring in the multiplication principle. The number of ways of choosing the 2 maths books, 4 choose 2, and the number of ways of choosing the 2 history books, 3 choose 2, gives me the number of ways I can choose 4 books. Let's work out this answer. 4 into 3 over 2 factorial into 3 into 2 over 2 factorial equal to 6 times 3 equal to 18 ways. This is important. What have we done here? We have used combinations for every subpart of the question where they are applicable. And then we have used the multiplication principle to combine all these subparts to get our final answer. You have 7 different maths books and 4 different history books. Then how many different ways can you choose 3 maths books or 3 history books? So again, the maths books will be chosen in 7 choose 3 ways, maths. The history books will be chosen in 4 choose 3 ways, history. And let's just apply the multiplication principle. Well, let's not, because we're not choosing 3 maths books and 3 history books. We aren't choosing 6 books. We're choosing just 3 books. So we have either the 7 choose 3 ways of choosing the maths books, or we have the 4 choose 3 ways of choosing the history books. What's the total number of ways? 7 choose 3 plus 4 choose 3. We want either 3 maths books or 3 history books. You have 7 different maths books and 4 different history books. And how many ways can you choose 3 books if you must have at least 1 maths book? Okay, interesting. You must have at least 1 maths book. What does this mean? I need to break this up into many scenarios I can understand. At least 1 is a fairly complicated term. It means I could have 1 math and 2 history. Or I could have 2 maths and 1 history. Or I could have all 3 maths and no history book. Because they want at least 1 math book. Okay, let's do all 3 of these. Now we have a grip on the problem. We can actually do each of these subparts. 1 maths and 2 history would be 7 choose 1 times 4 choose 2. I'm picking the 1 math book out of the 7 math books. I'm picking the 2 history books out of the 4 history books. Since I want a math and 2 history, the multiplication principle bails me out and I multiply the 2 sub-answers. Similarly, if I want 2 math and 1 history, 7 choose 2 times 4 choose 1. And if I want all 3 math, it's just 7 choose 3. What do I do with these 3 answers? Well, these are 3 separate scenarios. It could either be 1 math and 2 history, or it could be 2 math and 1 history, or it could be 3 math. So I add all 3 of these answers to get my final answer, which is 7C1 into 4C2 plus 7C2 into 4C1 plus 7C3. It's important to break it up into cases, then each of these sub-cases makes sense. We have built up on our previous problems to be able to solve this problem. You have 7 different maths books and 4 different history books. In how many ways can you choose 3 books if you must have at least one of each subject? What are the situations I'm allowed? I'm allowed 1 math, 2 history, or 2 math, 1 history. So this is actually a subset of the previous question. 7C1 times 4C2, and this is 7C2 times 4C1, and you add both answers. Look, let me quickly work these numbers out. 7C1 is 7, 4C2 is 6, 7C2 is 21, 4C1 is 4. So the final answer is 42 plus 54. That's 126 ways. So there are 126 ways where you can have at least one of each subject. Moving on. You have 5 shirts, 4 pants and 6 hats. Then how many different ways can you choose 3 shirts, 2 pants and 3 hats for a weekend trip? So you need to choose 3 shirts out of 5 shirts. That's 5 choose 3. You need to follow that up by choosing 2 pants out of 4 pants. That's 4 choose 2. And you need 3 hats out of 6 hats. That's 6 choose 3. Since you need the 3 shirts and the 2 pants and the 3 hats, the multiplication principle is applicable. And this is your final answer. What's 5 choose 3? Well, I'm going to be clever. 5 choose 3 is the same as 5 choose 2, which is 10. What's 4 choose 2? That's 6. What's 6 choose 3? Well, that's 6 into 5 into 4 over 3 into 2 into 1, which is 20. So the final answer is 60 into 20. That's 200. So there are 1200 ways in which I can pick 3 shirts, 2 pants and 3 hats from the wardrobe just described. Let's go back to the Jeep problem we saw earlier in the permutations class. Let's change the problem to a selections problem. A Jeep can accommodate 5 passengers, including the driver. Suppose there are 8 friends and 3 of them know how to drive. In how many ways can 5 of the friends be selected for a trip? So I need to choose 5 friends out of 8, and only 3 of them know how to drive. So I must pick at least one driver. Again, I can do this case-wise. Driver and others. So I could pick one driver and 4 other friends. Or I could pick 2 of the drivers and 3 other friends. Or I could pick all 3 of the drivers and 2 of the other friends. Now I've broken them down into situations that are handleable. The first case can be done in 3C1 into. Now those other 4 friends are being picked from the friends who do not know how to drive. And there are 5 such. So into 5C4. 2 drivers can be picked in 3C2 into 5C3. That's the other 3 friends from the 5 friends. 3 drivers can be picked in 3C3 times 5C2 for the other 2 friends. So we just add up these 3 ways of doing it and we get our final answer. Let's quickly calculate it. 3C1 is 3, 5C4 is 5, that gives me 15. 3C2 is also 3, 5C3 is 10, that gives me 30. 3C3 is surely 1, and 5C2 is the same as 5C3, so that's also 10, that gives me 10, and the total is 55 ways. So I broke down the problem into cases. Since drivers and others were differentiated, I broke them up into the number of drivers I can select and the number of others I can select. And they should total 5 because I need to select 5 friends. Let's approach this another way. Since I must pick at least one driver, let me calculate the number of ways I can pick no driver. So if I pick no driver, that happens to be 5 friends have to be chosen from among 5 friends, the 5 who don't know how to drive. And that answer surely is 1. 5C5 equal to 1 for those who've begun to rely on formulae. Now, this is the number of ways where no drivers are picked. If I subtract this from the total number of ways I can pick 5 friends from 8, then the rest of the ways will contain ways where surely there is at least one driver. So, the total number of ways I can pick 5 friends from 8 is simple. It's 8C5, and I subtract the number of ways no drivers can be picked, that is 1, and I should get the number of ways where I can pick at least one driver. So this is equal to the number of ways containing at least one driver. Let's calculate this. 8C5 is the same as 8C3, so it's 8 into 7 into 6 over 3 factorial minus 1. That's 56 minus 1 equal to 55 ways. Wonderful. I get the same answer no matter what approach I take. Let's move on to something more subtle. So far, we've been selecting from objects that were distinct. For instance, we picked from people, we picked from letters A, B, C, D, E, and so on. Now we are going to pick from a set of objects where objects are repeated. So several of those objects are indistinguishable. Thinking about it, it's quite clear that now many of our earlier selections will again compress to the same selection because the same object is being picked in many different ways. So let's look at a simple example. How many different selections of 4 distinct letters are possible from the letters AA, BBB, CDE? To bring out the contrast, let's assume that all these letters were different. Then I would have 1, 2, 3, 4, 5, 6, 7, 8 different letters. 8 distinct letters. Choose 4. That answers 8 choose 4. That's a question we've treated many times earlier. Now the letters are not distinct. There are 2 A's, 3 B's, a C, a D, and an E. So among these 8 letters, how many distinct letters do I have? I have just 5 distinct letters. an A, a B, a C, a D, and an E. So we have 5 distinct letters. And the number of ways to choose 4 distinct letters from 5 distinct letters is 5C4. So you see, when letters are repeated, the choices drop dramatically. If all the letters were distinct, we would have 8 choose 4 ways of choosing 4 distinct letters. With letters being repeated, we now have only 5 distinct letters in this particular case, and so the number of ways of choosing 4 letters drops to 5C4. Let's stay with this example for a while. How many different selections of 4 letters consisting of 2 distinct pairs of identical letters are possible? From the letters A, blah, 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 blah. Okay. So I want 2 distinct pairs of identical letters. What does this mean? So I want something like AA, BB, or a FF, AA. Of course, since I'm selecting, any permutation of AABB will be counted with AABB. It will not be a separate selection. Certainly, I cannot have AADE because D and E is not a pair of identical letters. So, how many different letters do I have in all from which I can choose? Well, there are 2 A's, there are 3 B's, there are 3 C's, and there are 2 F's. So these 4 letters can provide me with a pair of letters. The letters D and E cannot operate in this scenario because there's just one of each. Now the question has been simplified. I have 4 letters which have enough copies to make a pair. I have 4 letters and I need to pick 2 letters out of them. Why just 2 letters? Because when I pick an A, I know I'm going to pick 2 of them. I need a pair of identical letters. When I pick an F, I'm going to take 2 F's because I need a pair of identical letters. So the problem boils down to picking 2 distinct letters from the 4 distinct letters A, B, C, and F. And that answer is easy. 4 choose 2. So there are just 4 choose 2 ways of selecting 2 distinct pairs of identical letters. Hey, but there seems to be a problem. 4 choose 2 means choosing only 2 letters, but I need to pick 4 letters in this question. Yes, but when I choose the 2 distinct letters, I then take 2 each of them. And that doesn't add to the number of ways. For instance, if I picked A and C in the 4 choose 2 ways, this corresponds to AACC. That's actually the set I'm talking about, the set AACC. So the correspondence between picking 2 letters and picking 2 pairs of identical letters is established. How many different selections of 4 letters consisting of 3 identical letters and 1 distinct letter are possible? So I need to pick 3 letters that are identical and 1 other letter that is different from those 3. And how many ways can I do this? So let's again write out how many choices I have of each letter. I have 2 A's, 3 B's, 3 C's, 1 D, 1 E, and 4 F's. So let's look at some examples of the way we can pick. So I could pick 3 A's and a D, or I could pick 3 A's and a B, or I could pick 3 C's and an F, and so on. You can see that in each of these ways there are 3 identical letters and 1 other letter. Let's start counting them. Which of the letters will permit me to pick three of them? Those are the B's, the C's, and the F's. So I have three choices to pick my triplet from. In how many ways can I pick one from three choices? In 3, choose one way. Now that I've picked the letter which I will repeat 3 times, I have to pick the other letter. How many letters do I have in total? I have 1, 2, 3, 4, 6 distinct letters, A, B, C, D, E, F. And I've picked one of them to be the triplet. So I can't pick that again. So now I have 5 choices for the fourth letter. In how many ways can I pick that letter? 5, choose one. Since I'm picking the 3 letters and then following up by picking that 1/4 letter, the total number of ways is 15. Again, think about it. 3C1 means picking one letter. 5C1 means again picking one letter. How then do I have 4 letters? Because this 3C1 denotes the triplet. So whichever letter I pick here will actually be repeated 3 times. The 5C1 denotes the fourth letter that I am picking, which must be different from the triplet. Okay, now it's open season. How many different selections of 4 letters are possible from the following sequence of letters if repetition of letters is allowed? So I'm allowed to pick any combination of letters and any way possible. Again, I need to first list how many of each letter I have. So I have 3 A's, I have 2 B's, I have 1 C, I have 1 D, I have 2 E's, and I have 1 F. So can I take 4 of one letter? No, I can't, because I don't have 4 copies of any one letter. So that's out. What can I take? Can I take 3 of one letter and 1 different? Yes, that seems possible. So let me write that. 3 and 1. In how many ways can I do it? Well, there's only one letter that's represented 3 times, the A. So I have only one choice, 1 choose 1 for the triplet, following which I have B, C, D, E, F, 5 choices for the second letter, which will be used only once. So in this combination, which is a triplet followed by one letter, I have 1C1 times 5C1 equal to 5 ways in which to do it. Is there another way of picking 4 letters? Yes, I could pick 2 of one and 2 of the other. That means 2 pairs of identical letters. How many choices do I have to pick pairs? Well, the A's, the B's, and the E's are all appearing twice. So these are the letters that will permit me to take 2 of them. I have to pick 2 such pairs. So that's 3, choose 2. 2 such pairs out of 3 pairs. That answer is 3 ways. Again, note, in 3 choose 2, I am choosing only 2 letters. But I will take both copies of those letters to make up my 4 letter selection. Is there another way I can pick 4 letters? Yes, all 4 distinct. 4 distinct. How many distinct letters do I have to pick from? A, B, C, D, E, F. I have 6 distinct letters to pick from, and I need to choose 4 of them. That number of ways is 6 choose 4, which is the same as 6 choose 2, which is 15 ways. So I've broken it down into all cases. A triplet and a solitary letter, 2 pairs and 4 distinct. There is no other way I can do it. The final answer is 23 ways. This is a very important example because it brings together everything we have learned so far. I've broken it up into sub cases where I pick some indistinguishable repeatedly and others. The only case that was left out here was where all four letters could have been the same. That wasn't possible in this particular example because I did not have four of any one letter. If that was there, then I would need to count that too. Which brings us to the next example. How many different selections of four letters are possible from the letters A, B, C, D, E, F, G if repetition of letters is allowed? So here I need to be careful. Here I can take four of one kind, I can take 3 and 1, I can take 2 and 2, and I can take all four different. And I need to count each possibility separately. So let's do that. 4 of a kind. 4 of a kind means I need to pick one of these letters and then take 4 copies of them. How many letters are there? 7. So I have 7 choose 1 equal to 7 ways of getting all 4 which are identical. Let's do a 3 and a 1 breakup. That means I want 3 letters which are identical and 1 which is different. Since I have multiple copies of each letter, I have 7 choices from which to pick the letter which will be a triplet. So again it's 7 choose 1. And now that that letter is chosen, it cannot be chosen again. So I have 6 letters left from which to pick the singleton. That's 6 choose 1, which is 42 ways. How about 2 pairs of 2? Well, so here the situation is I need to pick 2 letters and each of these will then be represented by a pair. So I have 7 letters to choose from and I need to pick 2 of them. 7 choose 2, which is 21 ways. And the last possibility is all 4 distinct. In how many ways can I do this? Well, I have 7 letters and I need to pick 4 distinct letters. That's 7C4, which is the same as 7C3, which is 7 into 6 into 5 over 3 factorial, which is 35 ways. So the total number of ways of picking 4 letters when repetition is allowed is 7 plus 42 plus 21 plus 35, which I shall now add in my painstaking manner. That's 49, 50, 70, 105 ways.